is known as torque. Okay, now let's view this when it's not a torque. Okay, so now, right, so now let's say we view this in the XY plane. Okay, so we know on the XY plane, we'll sketch this out. This is our structure. Okay, so we're going to focus on the 500 pounds over here. Sorry, the 150 pounds. And then we're going to sketch our neutral axis. Okay, so that's our neutral axis. Then we have our element H. And then we have our element K. So during deformation, okay, our structure will deform like this. Okay, so this is where we have our 150 pounds. And if you look at our neutral axis, how is deformed, right? It looks like this now. Can you see the difference? Okay, so this is where it is a moment. Okay, so note during loading, okay, when the neutral axis is either a smiling face or a sad face, right? Then the loading, right, is known as bending moment. Okay, so you can see the difference now, right? Okay, so you have to focus at the position of the neutral axis. That's why when we started, I always emphasized on the position of the neutral axis, the position of the neutral axis. Okay, that is the critical part. So from here, we know, okay, so we're going to calculate the torque. Okay, so the torque is equal to 200 multiplied by the position of 100 of 10. So the torque is applied in the x direction. Okay, so finally you have Tx is equal to 150, right? Multiplied by 10 is equal to 1,500 pound each. Okay. Right. So this is where again the stage where students or even engineers, very seasoned engineers, make a lot of mistake or are not sure is when is it a moment and when is it a torque, first thing, and then the other one is what we have been through, right? Is the moment the perpendicular distance, is it towards the element or towards the neutral axis? These are the only confusing part. Okay, right. So we're going to do a very extensive example. Okay, we're going to analyze the structure and we're going to apply what we have learned. Now, this topic over here requires a lot of analysis. Okay, it's not just plugging in the right formula, it's the analysis that's critical. Okay, let's do a example. I'm going to start from a new page. Anyone, any questions so far? Okay, I don't hear anything, means it's fine. So let's look into example number 1. Okay, now I've posted this example on Avenue to Learn. You should go to Avenue to Learn to load the image, everything. Okay, so let me copy. Let me blow this up so one can see. And then I'm going to hey, oops, I do apologize. I think I just clicked something in accident. Can you still see my screen? Oh, you can still see my screen. It's me. And this is an important table. Okay, so let's look at a real structural problem. Okay, that is in compound loading configuration. Okay, so you can see that 4 forces are applied to a W200 by 41.7 roll beam as shown. Determine the principal stresses and the maximum stresses at point A. And I'm going to do something further. Okay, we're not going to just look at point A. We are also going to look at point B. And let's do all at the same time. Okay, so we have point A and point B. Okay, so point A and point B are positions here and here. Okay, and then the beam that we're going to use is W200 41.7. So you go to a table. Okay, so we identify what we are looking at. So we know that this will be our W200 41.7. So this is the data that we're going to use. Okay, these are the data that we're going to use. Okay, so you can see the data that we have. Okay, so what is provided are these data. So what is provided are the cross-sectional area, the depth D. So this is what do they mean by depth D. Then remember I got you used to the term flange and web. So now you know what is a flange. So now you know what's a web by looking at the structure. The horizontal part is the flange for this case. The vertical member is the web. So we know what is the width of the flange, which is our BF, right? Then thickness is the TF. Then we have thickness of the web, okay? And then we have second moment of area, IX. We have S. Now S over here is basically, wait, let me try to recall. Okay, it's basically I, right? I over Y. Okay. And then you have your radius of gyration over here. Now you'll be wondering what is the why is the radius gyration provided? We tend to use this for buckling analysis, which I will teach in week 11. Okay, so same thing for the y. You have along the y-axis you have your IYY. Okay, the I over Z for the SY, and then you have your radius of gyration. So this is what this table means, right? So the question state that we have to find the stresses on element A, as I said, and we are adding B. Okay. So the first thing you have to verify, if you have to look at the transformation over here, right? This is your X and that's your Y, and over here there's also your X and that's your Y. Make sure they are the same. Then you know what is your IXX and IYY. So the first thing you do, you know that your IXX is equal to 40.8. Yeah, is equal to 40.8 times 10 to the power minus 6 meter 4, and then your IYY is equal to 9.03 times 10 to the power minus 6 meter 4. Okay, then from here we're going to draw our transformation. So our transformation, as you can see, relative to what is given, okay, in the cross section. So we know that this is our X. Over here, this is our Y. Okay, and then we apply the right hand rule, right? So going vertically up, this is our Z. So what we're going to find is, based on what we have seen, we are going to use the formula. Okay, so we are going to find our stress Z, our normal stress in the Z direction. Okay, stress Z is equal to PZ over A, right? Plus by my or mx over ixx multiplied by y plus by my over iyy multiplied by x. So let's see what are the things that we can get from the table. We found our ixx, we found iyy. Next we need to find our a. So A is our cross-sectional area, so it's given as 5320. So A is equal to 5320. Because it's in millimeter squared, you must times 10 to the power minus 6 meter squared. Okay, so that's your A. And then the next formula that we're going to apply is we're going to have our we're going to have our shear stress. We don't know what direction the shear stress is yet, but the general formula is, because Z, okay, is the if we draw the position of our neutral axis first, okay. So I'm going to draw the position of neutral axis. This is just a sketch, okay. Okay, so that is the position of our neutral axis. And the neutral axis is parallel to the z-axis. So the torque will be in the z-axis, right? Because if it's like if you see on the previous example over here, right? Over here, our neutral axis is in the x direction, right? So the torque that we calculate is in the what? X direction, okay? So that's why I did not mention this earlier. My apologies, okay? So over here, you know that torque is in the z-axis because that is the direction where the neutral axis is parallel to the axis is z. Okay, so multiply by c divided by j plus by vx over iyy qy divided by t plus by vy over ixx Qx divided by T. Okay. That's where you see, oops, my computer crap out again and come back in.